There you go. Let's prepare for cloudy and absorption lines.
Okay, hi everyone. We are Group 3, Cloudy Absorption Lines, and we were supervised by Xiao Wen Chen. And part of this illustrious group is Yunia, Francis, Florian, Joanne, and myself, Mikhail. And our hands-on project entailed using Cloudy to explore ionization fractions and cooling rates. But first, we have to ask ourselves, what is Cloudy? Well, simply put, Cloudy is a computer program with the ability to compute the physical conditions of diffuse gas. And it does this by running simulations and predicting the thermal, ionization, and chemical structure of gaseous clouds. It also has the added functionality of being able to predict features of absorption and emission in output spectra for further verification and visualization of your models. It's also extremely flexible, having the versatility allowing us with the freedom to change and constrain certain parameters, such as the redshift, the neutral hydrogen density, metallicity, and geometry. So that's what Cloudy is, but how does Cloudy work? This is a very good question, and I don't think our group is fully in tune with that. But anyway, so starting Cloudy, before we run it, Cloudy first needs a few things before predicting the conditions in the cloud and actually making a model. So what are these ingredients? Most basic ingredients are the number density, the abundances, controlling the metallicity content of our model, the geometry of a model, and commands to govern our output. And this in turn leads us to getting a cloudy model with physical conditions and also our output spectra where we can verify our models. So we decided to use cloudy and explore the ionization fractions in our models.
Right. So what Mikhail and I was most interested in was essentially the photoionization. So we were essentially exploring a lot of like parameters, like a subset of the parameter space, because we've seen that there's many input parameters, and one of those is, for the photoionization, of course, the spectrum that you irradiate your cloud with. And with cloudy, we had, like, amongst some others, three. Here we go. Oh, right one. So three incident spectra, SEDs, of which, you know, some of them include quasar and quason galaxies, and some of them like STB, the starburst model that models the distribution, the SED of a starburst galaxy close by. And I think the takeaway from this plot is essentially that if you compare this here, that you see that especially after the helium-3, after the helium-3 limit, you essentially with the starburst 99, you have really a lack of very high energetic photons. So your gas cloud, well, this will also have an effect on your gas cloud and on the composition of your gas cloud. So, right. Now exploring really like the parameter space a little bit with like the density, the hydrogen density, the metallicity of the cloud, as well as the limiting column density that Cloudy integrates over. You can see how the composition of the gas with respect to the ionization stages, like the ionization fractions, changes. So more specifically, here we have sort of a slice out of the cube that you can run overnight. It's very versatile. So that you can here see, like, if you vary the number density, the hydrogen number density, that you will also see the more dilute gas. The photons, the incident photons from the incident spectrum, they really have an effect and can ionize here, in this case, oxygen to very, very high ionization stages. In this case, for the HM12 model, and for comparison, you also have here HM05. And you can see that there's a little bit of a difference, and there's a little like funny feature here, which is like an artifact. So this was also during the process a reminder that you should not 100% trust whatever you're working with. Like, after all, this is a model, so, and you know, you might also encounter some oddities in there. And just because the most interesting part of that plot is in the upper left, we can also just zoom in and see how nicely we have many different ions present at different parameters for the density. And because I also just wanted to play around with the animation, you also see here a scan through of the oxygen ions that are essentially scanning through. And the takeaways is essentially the ionization fraction that is mostly affected by the gas density, by the incident radiation, and also not so much by the metallicity. Right.
So we also look into the cooling coefficient of different cooling efficiency of different elements. So from this, we need 3 different ingredients to calculate cooling efficiency. First is the ionization fraction and the cooling rate per volume of different ionization state of the elements, and as well as setting the number density of the gas. So we are only looking into ionization fraction from collisions. So it does not depend on the number density of the gas, but it does depend on the temperature of the gas, because the number of energetic electrons increase as temperature increase. So from cloudy, we set at a given set number density, we obtain the ionization fractions for every ionization state for the element of interest, and also the cooling rate per volume for separate ionization state. And Francis will show us that for carbon.
Yes, so I got carbon. Thank you. So these are our input parameters. Up here, we have our H number density, which, like we said, it doesn't matter particularly. We just set it to 1. Metallicity is solar. And what we did was vary the temperature between 10 to the 4 to 10 to the 7 Kelvin. And so what we obtained from that was the ionization fraction of all of the carbon ionization states here. And we can see very predictably that we get higher and higher levels as we increase the temperature. And then we calculated the cooling rate for each of those specific states, which is what you show up here. And then to get the actual cooling rate from these ions, we have to multiply them by the fraction here. And so we obtain from that these cooling rates, and we can see that the higher states dominate the cooling rate at higher temperatures. So we get this nice double bump feature as our total cooling rate for carbon. And Yunia will talk about oxygen.
So here we have essentially the same plots as before, just for oxygen. So oxygen has a few more ionization states, so the plots look a bit more messy. But yeah, they essentially show the same. Is that the, yes, that is. Okay. So yeah, here we see as well that at higher temperatures, the higher ionization states dominate. And again, when stacking up the cooling curves of the different ionization states that we see here, then we get that nice total cooling curve down here. And if we're now stacking both up, the oxygen and the carbon, you see it here on, yes, for you it's the right, in yellow the carbon and in blue the oxygen. And then we get that nice double peaked cooling curve here, which already assembles very much what you find in literature for cooling curves. We have an example here from Gnad and Sternberg 2007, and here you can already see this double peak in the solid curve for solid metallicity. This is what we run for carbon and oxygen, which is exactly at the same place and same cooling strength as we calculated it. And yeah, we would acquire the same cooling curve as this one here if we would have already run that full model for neon and iron and all the other elements as well. But that would have taken up too much time, so we didn't do that.
So as a summary, cloudy, super fun, super easy to use, but only if you manage to get it installed on your computer. It doesn't run on Windows. So Mac and Linux, it works. And it is also extremely well documented if you know which hazy document to look up what you're finding for, but you will get all your answers, questions answered if you know where to look up. And yeah, we managed to figure out how different incidence spectra used for cloudy will influence the ionization properties of the predicted output. We've also managed to replicate the peaks of the cooling efficiency curve for carbon and oxygen. With that said, we are definitely motivated to use Cloudy to answer more questions, and you can too. And that is all from us. Thank you.
Thank you, Cloudy Absorption Group. So questions for them?
Just out of curiosity, could you tell me what your stopping criteria were?
For which project?
Any or all, actually.
For the cooling stuff, I think we stopped at column densities of 15. That was our stopping criteria, 10 to the 15.
Okay,
Yeah.
and the others?
16.
So basically,
Like-
you just looked at where neutral hydrogen reached a particular column density. So that means you probably didn't go into like the molecular part of the cloud, and you still stayed somewhere on the atomic region of the cloud. Is that
That
right?
is sort of true for yes. The one plot that you have seen. Yeah, I guess this one. Like the very, very dense parts, like the temperatures are in this very case, like I can only speak for myself here, but in this very case, the temperatures here were pretty much at the order of like 10 to the 4-ish, all across the range here. So it was not molecular, to my knowledge.
All right. Thank you so much. Great work by the way.
Other questions for the Cloudy Absorption Group? And maybe I can get the next group 5 to come down. So question for you then. So especially for this one, the incident radiation field was kept constant, right? So then changing the density changed the ionization parameter.
Yes.
Okay. Any other questions? If not, let's thank the Cloudy Absorption Group again.